All right. So this is about the Navier Stokes equation. I don't know if I'm pronouncing that correctly. Navier Stokes equation, right? I watched a number file video talking about it, and this one guy, I thought he was funny, but he was talking about this, very passionate about it, loves this equation, right? And so the question was proposed that in a flow, like in an assumed incompressible flow, or a fluid, right? There, when you have a flow go around like a 90-degree corner, right? At the very point, you get a prediction from the equation. Everything else works out fine using this equation, but at that point, you end up with an infinity. And apparently that's a big issue, right? Because it's like, why does that happen there? And so I'm going to try and give my explanation of it because I was kind of curious. And a brief explanation of what I think it is I have two possible reasons. One, it's because you're assuming an incompressible flow. And by definition, by assuming an incompressible flow, you are creating this infinity because the reality is that, or an incompressible fluid, because by assuming the fluid is incompressible, you have put a limitation on, the fluid that's just not real, right? Because every fluid is compressible to a degree. And so potentially that's why you're getting this infinity showing up, right? And so that's a potential solution, simple, easy. It's just you're not using reality to. It's not real, right? So you're not getting a real answer. The other possibility is that actually doesn't matter, and what's happening here is that it keeps getting compressed. It keeps getting compressed down, but it doesn't change anything actually, because. What I mean by this compression is I'll just kind of explain. I'll try and show this drawing. It's a terrible drawing, to be honest. But if I zoom in here, right? So I'll try and show it to the camera. So imagine that this light blue section here that doesn't look all that different from the other spot. This is the corner, right? So right here where this arrow is at, we got this corner, right? And so as you can see, barely, I drew like a little swirly here. So pretty much what happens is the water comes up, right? And then it flows around this corner. And then it kind of flows down to fill this space. But then water flows in, or we'll just assume water, right? So the fluid flows in, right? And then it comes down and falls in. But the water that's over here gets kind of walled in by the water or the fluid that's over here, so it gets pushed back this way, right? And so as it gets pushed, as it gets pushed back this way, what happens is that it starts to form like a vortex. That's what this kind of purple area is here. It's hard to see. I drew a swirl in there, but it's black. And so we have a swirl, right? A vortex forms within this flow. Naturally, it just kind of comes out of this process, right? And so it's coming back, and as the flow continues, right, the fluid will slowly push this vortex towards, where the source is, basically, the water coming around on the other corner. It'll push it towards this corner until a point, because once it gets here, then all of a sudden, now you have this flow coming up, right? So it can't keep moving into the flow, so it gets trapped right here at the corner, where the flow's going by, straight up. But what happens is that as this flow is moving up, it is providing energy to, it is helping provide energy to the swirl, right, to propagate it longer. And all the energy on this, all the flow on this side is actually pulling away energy from this vortex, from the swirl, and is slowly reducing it. And so that's why it slowly moves this way. But once it gets to this point, it hits this point of potential equilibrium, right? Where you have this swirl getting constantly fed, but also, taking it away. And so what's happening here is it may not, it doesn't stay the same size and just swirl there, but the energy being added is not equal to the amount of energy being taken away. And so as time progresses, the vortex gets smaller and smaller and smaller until a point that it's not even noticeable anymore, right? But like I said, potentially this is where it gets compressed to a point and it should just disappear. But because it's an incompressible fluid, it can't, right? It can't disappear because you can't compress it enough to remove that motion. And that could be wrong. But if it's not that, then what's happening is that this vortex is constantly being eroded away, right? Slowly being eroded away. But this is kind of like a very interesting thing that I just realized is that it highlights infinity, because here's the thing. When you have energy, if that, like, any amount of energy is technically infinite, right? So no matter how long you let this flow continue for, at some scale there will still be that vortex, right? It'll be incredibly microscopic. It won't even, like, it could be going into what I believe reality is, right? It goes beyond the fluid. At that point, the motion is not in the fluid itself. It's in the dark energy or something instead. It just is slowly working its way down the scale, right? It's like, practically speaking, it's a smooth flow, right? It's a smooth flow. But from a mathematical perspective, the flow there continues to infinity as a vortex. The vortex getting smaller and smaller and smaller, but since it's approaching infinity, it can never actually reach it. And so you end up with this infinitesimally small point of infinite, vortex. And so that's where it's coming from, because just the nature of infinity, you can't actually, like, it has energy, and that energy, like, can be reduced, but no matter how much you reduce the energy, it is like, it's still always going to have energy. And basically you have a vortex that disappeared at our level, but it works its way down through the levels and just continues on forever. And it's such a weird thing, because it's like, okay, well, like, does any motion ever actually truly stop? Like, does every vortex, like, appear to disappear at our level, but it actually, vortexes down to infinity, right? Every time we see a swirl happen, the energy at our level is lost, right? And okay, then it goes back to a normal flow. But at levels below us, it's vortexing for infinity. It'll just keep vortexing forever. That, I would say, why not? Why wouldn't it? And that's kind of interesting, right? Like, our actions, like, every action that we take perpetuates energy down through infinity as it slowly is dispersed out, right? Every time I wave my hand, I have moved air molecules, right? And these air molecules in motion have created swirls and have dissipated their energy, and this energy has to be dissipated out now through infinitum, right? So every wave of my hand is actually going to perpetuate for infinity, right? The energy that I have just exerted is infinite. Not to us, but from a mathematical perspective, I have just exerted infinite energy. By just waving my hands around, I'm exerting infinite energy. And again, not infinite energy in a practical perspective, not infinite energy to us, but if you followed the dispersion of the energy, you could keep following it forever, because infinity is infinity, and there is always a smaller value, right? So if you started with 1, right, this was 1, well, then you could, like, in between 0 and 1, there is infinite points. And so, like, I don't know, infinity is so weird. But long story short, that's why I think that that's the case. It's because infinity is real. We live in infinity. And I think it's so funny that like so much of math is afraid of it. Like singularities can't possibly be a thing and all this stuff. Like when we see infinities, we're like, oh, we messed up. It's no good. And like in some cases, yeah, maybe that's the case. But I don't think it's a good habit to just assume every infinity that pops up is an error. A misunderstanding, sure, but an error, not necessarily, right? And so, yeah, I think that's all I really have to say on it. So, peace out.